I'm just reading the talk titles to see how prepared I am. I am prepared enough to get David Schaich's name right. And so if you welcome to the stage David Schaich, who's going to tell us about 5 minutes on the dark side of the universe.
Thanks very much for that warm welcome. This is my first time speaking here, and I'm also pretty new to Liverpool itself, as you all might have guessed from the noises coming out of my mouth. I am a theoretical physicist by trade, and I've spent the past decade applying that trade on both sides of the ocean. A few months ago, I managed to land at the University of Liverpool, where I hope to remain indefinitely. And I'm up here tonight because I believe that science is an integral part of society, and its benefits belong to all of us. My goal is to give a quick look behind the headlines for some prominent scientific issues. And if you don't care for those politics, I can add that the government is currently funding my research at the level of about half a penny per UK taxpayer per year. So if you want, you can consider this just getting your money's worth. Now, the science headline for tonight is dark matter, and I'd like to ask for a show of hands, who here has heard of dark matter before? Yeah, that looks like most of us, which doesn't surprise me. Not only does dark matter make up about 85% of all matter in the universe, it also has to be very different from any substance that we work with in our daily lives. It's dark because it barely interacts with light, or with X-rays, or radio waves, or us, or the Earth as a whole. And in the next few minutes, I'm going to summarize how we reached the scientific consensus that most of the matter in the universe is dark. The key is that, well, as with most things in life, XKCD provides the short answer, which is that dark matter fits the data. And the key is that there are many very different types of data that are simultaneously explained by the hypothesis of dark matter. Now, the first evidence for dark matter came from the fact that the outer edges of galaxies are moving more than twice as fast as they should be, which suggests that there must be much more matter than we can see to swing those stars around in the same way that the moon is swung around by the Earth. This sort of thing was first observed way back in the 1930s by Fritz Zwicky, among others, but for many decades, people made the reasonable assumption that something boring and ordinary was just being overlooked. It wasn't until the 70s that Vera Rubin, among others, completed all of the careful checks needed to be confident that something new and unusual really is going on. Of course, the 70s was just the start of the story, and since then we've gathered more and more evidence that this new and unusual phenomenon is in fact dark matter. And the key is that dark matter produces consistent effects across a vast range of length scales. So if we move up to look at lengths about 1,000 times larger than galaxies, we can see how the presence of matter curves space like a lens. This is shown in blue in this picture, while X-rays coming from the ordinary matter that we're familiar with are colored pink. And this makes it clear that most of the total matter is thousands of light years away from the ordinary matter that we can see. Going higher to length scales about 1 million times larger than galaxies, we can run computer simulations of how the large-scale structure of the universe formed over time. Now, if we don't include dark matter in those computations, we end up with simulated universes that look completely different from what we see in the sky. In fact, even if we do include dark matter, but we make it too hot, we end up with very different looking universes. So, even though this discussion might feel very out of this world, it's useful to appreciate that without dark matter, the Milky Way as we know it would not have formed, and, well, we would not be here tonight. So finally, let's wrap up by looking at the largest length scales in the observable universe, spanning more than 10 billion light years. The different colors in this picture show fluctuations in the temperature of the universe, and the pattern of how areas of different temperature are spread out across the sky depends on the amount of dark matter that there is. And this is actually the data that tells us most precisely there's about 5 times more dark matter than ordinary matter. And that's the story for tonight. You now know the main evidence leading to the conclusion that about 85% of the matter in the universe is dark and why that matters. Please let me know if you found this a worthwhile 5 minutes, and if so, we might do it again in the future. Thank you.